There are many different types of classifiers to choose from. Briefly, I'm going to go over the model we'll be using, the support vector machine, or SVMs. The solid line in the middle is the decision boundary. Any observation that falls on one side or the other belongs to a different group. The neat thing about SVMs is that the model allows itself to have incorrectly classified observations. The dotted lines are called the hyperplanes, which the support vectors push on to adjust the optimal margin between the groups in the decision boundary. Well, that's a brief introduction to SVMs. There's a lot more to them, but let's get to the code.
So we finally got to the part you've probably all been waiting for, the actual classification model. The model we will be using is called a support vector machine. This is a very common model used in neuroimaging. Specifically, we're going to be using it with a polynomial kernel. The kernel determines exactly where that data point will be placed relative to the hyperplane. So sex is going to be the variable that we're going to be predicting, and then I'm going to feed in my trained data set, and the method is going to be support vector machine polynomial kernel, and I'm going to allow a tune length of 5, which means 5 degrees, so 5 degrees of polynomials. And then the metric we're going to use to choose the best tuning parameters is going to be the ROC curve, and I'll explain what that is in a blog post. And for pre-processing, within each cross-validation set, we're going to be doing demeaning and scaling. The reason it's important to do pre-processing within your cross-validation sets is because, think about it, if you subsample your data set, the mean and the standard deviation is not going to be 0 and 1 anymore, it's going to be something else. So we can just go ahead and look at our model, and we can see the tuning parameters that it has chosen. Degree equals 2, so it's going to be a second degree polynomial kernel, and the scale is 0.01, and the cost is 0.5. I'll explain what these mean in my blog post. We can also plot the different tuning parameters of our model that were used in the cross-validation and see how that affected the ROC scores. We can also plot variable importance for the model in a lollipop graph. This doesn't actually tell us what is the most predictive of all features ever. It's just for what's the most predictive feature for this model, or what are the most predictive features for this model. Okay, we successfully trained our model, and now the next step is to see how it does on an independent data set, which we don't have, so we just did a holdout set instead.